This video is about Lab 4, which covers oscillations. The purpose of this lab is to understand and predict a two-dimensional spring mass motion, a mass that both swings in an arc and stretches and compresses the spring, by combining video analysis with computational modeling. The final goal of this lab is to determine whether the model follows the energy principle. The main fundamental principle that we need to understand for this lab is energy conservation, which states that the total energy of the system remains constant over time, with energy only changing forms such as between kinetic, gravitational potential, and spring potential energy, but never being created or destroyed. And here are the important equations to understand for this lab. There are the spring force equation, the spring potential energy equation, the kinetic energy equation, and the gravitational potential energy equation. These equations are needed as they allow us to model and verify energy conservation in the lab. Lastly is the spring constant equation, which will be used later to calculate the spring constant using the period from the tracker video. And here's the procedure for my experiment. The system that I chose was the mass, the spring, and the earth, and the surrounding is everything else. I chose this system because, based on this system, there should be no outside forces acting on the object. Thus, there is no work done. Thus, the change in energy is zero. To begin, I first imported the video into Tracker to observe the position of the mass over time. Next, I edited the starter glow script code to match the initial conditions given by Tracker. Then, I compared the differences between the graphs generated by the computational model versus those by the observed data. Then, I plot the changes in energy and observe whether energy was conserved. And here are the initial conditions what I found from my Tracker video. First, the stretch length of the spring was 0.7 meters. The mass was 0.42 kilograms. The initial position is that, and the initial velocity is 0, 0, 0. The period which I found by comparing the peaks on the Tracker graph and finding the time between each of those and finding the average, which I found to be 0.61 seconds. K, which I found by using the formula described before, and then L, the relaxed length of the spring, which I found by taking the forces when the spring was relaxed, adding them up and solving for the relaxed length. In my code, I start by setting up the timing with t equals 0, with a small time step, delta t is equal to 1 divided by 210. Then I define the initial conditions, which I found from the previous slide through my Tracker video. Next, I calculated the spring stretch and direction using L, L hat, and S. Then I find the system's energies, kinetic, gravitational potential, and spring potential using their respective formulas. And then I added them up for the total energy. Inside the main loop, I calculate the gravitational and spring forces and add them up to get the net force, and using the Newton's second law to update the ball's velocity and position. After each step, I update the spring's geometry and recalculate the energies to check if total energy stays constant. And here's the final result. The two graphs compares the x and y position of the computational model versus the observed data. And as you can see, although the observed data and the computational model are quite similar at the beginning, the observed data deviates farther and farther away over time. This is due to the fact that in real life, the system is not isolated, and there may be other unknown forces doing work on the object. In addition, there is also error from me placing where the center of mass is on the Tracker video. Now we need to answer the question of, is the energy principle satisfied? And yes, the energy principle is satisfied because the total energy of the system remained nearly consistent throughout the motion, with only small variations likely due to measurement or computational errors. This can be seen from the graph as the total change in energy is nearly consistent throughout the graph, as 0. Lastly, I'll be comparing the oscillation periods depending on whether it's in the x or y direction from my Tracker video. I found that in the x direction, the oscillation period was 0.614 seconds, while in the y direction it was 0.519 seconds. The different direction give different periods of oscillation, which ultimately affects the spring constant and the graphs, as the spring constant is calculated depending on the oscillation period.